All right, let's jump right into this. Welcome to our latest explainer. Today, we're going to dissect a piece of tech that is probably sitting in your pocket right now, the iPhone 13. But we aren't looking at the screen or the camera. We're zooming way, way in to focus on one specific, incredibly vital element. It's an invisible pathway inside the device that literally brings it to life. But crazy enough, it's also the exact reason it can just completely die on you. We're going to demystify the absolute most crucial, wide-reaching power line in the iPhone 13. Technicians call it the PP_VDD MAIN.
So what makes an iPhone 13 instantly go completely dead? I mean, it's the ultimate repair mystery, right? Imagine you've got this perfectly good functioning phone and then, boom. In the blink of an eye, it is totally unresponsive. Just a completely dead brick. What actually causes that? Well, surprisingly, it's almost never a catastrophic failure of the main processor or a completely destroyed battery. Now, more often than not, the culprit is just a microscopic short circuit on a single, invisible line hidden deep inside the board. And yep, that line is the VDD_MAIN. To understand how one tiny little error can take down an entire smartphone, we've got to understand how this power line operates. To really wrap our heads around this intricate circuitry, it helps to think of the logic board kind of like the human body. Just as your heart pumps blood through a massive network of arteries to keep your organs alive, the iPhone has its own central bloodstream, the VDD_MAIN. It is constantly delivering life-giving voltage to almost every single corner of the device. And its heart? Well, in the iPhone 13, that's a very specific integrated circuit, or IC, known as the BPIC U4200. It literally pumps that voltage out to the rest of the board. Now, what is truly staggering here is the sheer scale of this network. 35. That is the number of pages in the official technical schematics dedicated entirely to this single power line. Think about that. When engineers map out the VDD_MAIN, it spans 35 pages of dense, complex diagrams. It touches so many components, branches off into so many subcircuits, and feeds so many chips that it's widely considered the most extensive power route in literally any iPhone model, past or present.
Okay, origin and flow, the heart and the blood of the logic board. We know it's a massive network, but where exactly does this bloodstream begin? Let's trace it back to the source.
So the VDD_MAIN doesn't just magically appear out of thin air. It has to be carefully generated. Its primary origin point, like we mentioned, is the BPIC U4200, which was actually an IC newly introduced in the iPhone 13 architecture. But this heart doesn't work alone. It interacts closely with another chip called the U4000 Rubicon, which handles charging, and it relies heavily on a cluster of 7 absolutely crucial inductor coils. And just like a real heart needs its own blood supply to pump, the BPIC requires input voltages to do its job. Specifically, it needs juice from the battery itself called VBAT, and a sensing line called PP_VDD_SNS_BPIC. If even one of those 7 inductor coils fails, or if the input voltage drops, the entire VDD_MAIN fails to generate. Simply put, no heartbeat, no life. And here is a super fascinating detail. The voltage flowing through this line isn't just some static number. It is a living, breathing metric that literally fluctuates in tandem with your battery's lifespan throughout the day. When you wake up with 100% full charge, the VDD_MAIN is pumping at roughly 4.2 volts. By midday, as you watch videos and scroll and drain the battery, that average pressure drops down to around 3.7 volts. And when you hit that critical 2% red line, the VDD_MAIN is running at about 3.2 volts. Actually, the phone shuts off entirely before it ever reaches 0 volts, usually halting right around 3.2 just to protect the whole system. So let's look at the vital organs, mapping power distribution across the board. The heart is pumping, the pressure is fluctuating, but where does all this power actually end up going? Let's separate the absolute life support systems of your phone from the secondary features. First and foremost, the VDD MAIN absolutely must feed the core organs. These are non-negotiable. It flows directly into the main IC power, which then distributes power to the CPU, the actual brain of the device. The CPU cannot generate its own power. It relies entirely on this flow. On top of that, the VDD MAIN supplies the baseband power, specifically the UBB-PMU E-chip. This is incredibly critical. Without this, your phone loses all cellular network connectivity, it loses its unique IMEI identifier, which is essentially its digital fingerprint, and the modem firmware just straight up fails. If blood stops flowing here, the device is functionally brain dead.
What's really interesting here is how highly adaptable the system is. Not every organ in the iPhone needs the exact same blood pressure, right? So the board uses these tiny regulators. Step-up circuits take that base voltage of around 4 volts and boost it way up.
For example, your display needs really powerful voltages, sometimes even negative voltages from -6 to -9 volts, just to light up your screen and register your touch. The camera flash, that also needs a massive step up to ignite. On the flip side, step-down circuits reduce the voltage so it can be highly efficient, which is crucial for components like the envelope tracker.
And a brilliant example of this smart distribution is that envelope tracker. It acts as a step-down regulator that feeds the power amplifier for your cellular signal. Basically, if you're standing right next to a cell tower, your phone doesn't need to scream to be heard, so the envelope tracker steps the VDD_main voltage way down, which saves your battery. But if you're miles away out in the countryside, it steps the power up so your phone can actually reach the tower. It's this dynamic, real-time power management driven entirely by that single VDD_main source.
Beyond those vital organs, the VDD main also branches out to power the extremities, the secondary organs. It feeds the U8300 Taptic engine, which gives you those nice, crisp vibrations. It powers the top and bottom audio amplifiers, so you can actually hear your ringtones. It reaches all the way to the 2.4G and 5G Wi-Fi modules, the NFC system so you can tap to pay, and it even powers your Face ID sensors. And hey, if you have a Pro model, the VDD main has to feed extra chips, like the U5600, just to handle the intense power demands of those advanced, high-resolution camera lenses. It literally touches everything. Right, moving into the diagnosis, troubleshooting a dead phone. So we know it powers everything from the CPU brain all the way down to the vibration motor. But what happens when things go wrong? Well, there is a pretty harsh reality in modern repair. If there is a short in just one tiny microscopic capacitor, the entire phone instantly stops working. Because VDD_main is a single, continuous, highly integrated line, a failure anywhere brings down the whole ship. If just one microscopic capacitor out of the hundreds attached to this single line shorts out, it drags the voltage of the entire VDD_main straight down to zero. The heart stops pumping, the CPU loses power, the phone instantly goes completely dead. Trying to find that one bad capacitor, it's literally like finding a needle in a high-tech haystack. And fixing this introduces a massive mechanics dilemma. See, modern iPhones use a sandwiched logic board, which is basically two boards soldered perfectly on top of each other. Now, this saves a ton of space and allows VDD_main to flow everywhere seamlessly, but it completely hides all the vital test points on the inside. To see those hidden inner points, technicians have to physically melt the solder and split the boards apart. But here is the major catch. The moment you split the board, you sever the physical connection. The VDD_main is generated on one half of the board, so the other half suddenly has absolutely no power flow, making it incredibly difficult to test the system under normal working conditions. Because splitting the board is so incredibly risky, technicians have to follow a highly strategic, non-invasive procedure first. Step 1, they probe exposed test points on the outside of the board. Step 2, if necessary, they'll carefully scrape away outer coatings just to expose raw copper. Step 3, they run thermal checks or diode mode testing to see if anything gets unusually hot. And only when a short is absolutely 100% confirmed do they take that final, risky leap to step 4 and actually split the board.
It's pretty amazing when you really zoom in, isn't it? A device that connects you to the whole world, manages your finances, and captures your best memories, all relies on a singular microscopic flow of voltage that constantly fluctuates throughout the day. It just takes one tiny flaw on a 35-page circuit schematic to bring the whole thing crashing down. It really makes you wonder, if a microscopic short can kill our most vital devices, how deeply do you understand the fragile, intricate technology sitting in your pocket right now? Definitely something to think about the next time your phone's battery dips below 2%.